Hello, I'm doing a walkthrough of the CSM final review worksheet. There's a bunch of problems, and I might not get through all of them, but let's see what we can do. So just if you want to skip around, the topics include environment diagrams, then we go to recursion, object-oriented programming, something about W-linked list, trees, generators, iterators, scheme, and then SQL at the end. Okay, so yeah, we're going to start all the way at the front at environment diagrams. So basically we have some function, and this one looks like it's just with a bunch of lambdas and yeah, mostly the midterm one stuff. Yeah, so let's get started. Let's just make our global frame right here, global. Okay, so the first thing that's done is this line here is executed, and that creates a function f bound to the name f. So function with intrinsic name f that takes a parameter also called f, great, whose parent is the global frame, the frame in which it was declared. Then we skip all of these lines here because they're part of the body of the function, so we don't really care about those until the function is actually executed. And then we say rebound f to the result of calling this expression. Rebind. So we can't actually rebind it until we evaluate this expression. So let's see how to evaluate it. Well, the rightmost thing is the argument that's being passed in. So that means this thing on the left, that must be a function. So the first thing we're going to have to do is evaluate the operator, which is this function. So to evaluate this function, we're going to open a new frame. So once we evaluate this function, we're just going to call it onto and then bind it to f. Okay, so I'll open a new frame, call it frame 1 of the function f, whose parent is the global frame. And then the parameter that it takes in is called f as well, and that parameter is 61a. Okay, now what does f do? Now we get to executing the body. Well, it defines a variable h and a variable g, both functions. So let's define them. H is a function h that takes x, y, whose parent is the frame it was declared in, so that's f1. Then g is a function g that takes in y, whose parent is also f1. And then we actually return the result of this complicated expression. So let's follow our same rules. The first thing we do is evaluate the operator, and then we evaluate each of the operands one by one, right? So let's evaluate the operator. The operator is just this function h. So let's make like a little note. Let's make this h blue, and then we'll say this h operator is this function right here. Okay, just for our memory's sake, this actually isn't part of the environment diagram. Okay, then we evaluate the operands. So the first operand is the g of sarcasm. So that requires us to open a new frame, g, whose parent is f1, and we got that from right here. And then the parameter that it takes in is sarcasm, and that's called y. Great. So that's sarcasm. And what does it return? Let's see. So this is actually a somewhat complicated body. The first thing it does is it declares g and h non-local. So that means that we're going to look in the parent frame of f2 and see if we find a g and an h. And we actually do. So instead of changing a g and an h in f2, we're actually going to be changing the ones in f1. So maybe let's star these. Okay, now we're going to reassign g to a lambda function. So it's now going to be a function lambda that takes in a parameter y. Okay, and the parent is now f2 because we actually defined it in f2. even though we're changing it in F1. Okay? And now we're reassigning h to a lambda that takes in 2 parameters. All right. So remember when I put this pointer to like this old h in the blue? That was because h is getting reassigned here. And we're going to actually lose like what this operator was if I just erase it. So what I'll do is I'll try to move this somewhere. So let's move this to like the top somewhere so we still remember this. Okay. Now, oh, we lost a little y. Oops. Okay. Now we say h is a function lambda with x and y whose parent is f2. Okay, so those are done and we just have to return something. We return y, which is sarcasm, indexed at 3. So our return value is going to be, so this is 0, this is 1, this is 2, and this is 3. And then add that to, oh sorry, I don't know why I wrote 3. The 3 is a C. Add that to 5:8. So that means we start at 5. So this is 4, and then in the orange is 5, which is this S. Then we go all the way, but not up to 8, not including 8. So we include 5, 6, and 7, but not 8. So that means we have C plus SM exclamation. Look at that. We have CSM. So that's our return value for our first function. Then we evaluate g of y. And notice this g actually changed. So we have to basically remember that. And now we're going to look up this g here. So we'll open F3, and g is now this lambda function. So the name g is bound to this lambda function that takes in the parameter y, whose parent is F2. Okay. And then we just want the parameter y here. And what are we calling it on? We're calling it appropriately on y. So hopefully that's a hint that we are going in the right direction. All right. So then what does this lambda function do? Well, it just slices y all the way up to index 4. So that means it's going to keep index 0, 1, 2, and 3, which is actually all of them. So this is just going to return y question mark. Okay, so we have both of these, and now we have to apply h onto these. So that's going to be f4, which is going to be our function with intrinsic name h, and 2 parameters x and y, which are both of these, so g of sarcasm and g of y. So g of sarcasm gave us CSM exclamation, and g of y just gave us y question mark. So this function h returns, let's see. So it's this function h right here. It actually assigns a variable z. So it says z is equal to 4. And then it returns a lambda that takes in a parameter z and then does something. So this return value is just going to be a func lambda whose parent is where we declared it, so f4. Okay, and it takes in a parameter z, so maybe I should indicate that. Sorry, it's tiny. All right, so now we have the result of all of this, and that's going to be returned in our call to f. So the return value here is also going to be this lambda function. And that means we've evaluated this f61a successfully. Now all we do is call that lambda with the argument 2. So I open an f5, and then lambda parent is equal to f4, and what's the argument called? It's called z. Z is now 2. And then we return x plus y. So x and y are looked up in the parent frame, where they are CSM exclamation and y. So x plus y is going to be CSM exclamation y question mark. And then we're going to multiply that by 2. And multiplying is just going to replicate it that many times. So replicating it twice is just going to be CSM y, CSM y. And that's what we're going to return. So let's see if we can just move that into our box here. Oh no, shit. Okay, let's just pretend I moved it there. And then that's actually what the last thing we have to do is bind f to that result. So this is also going to be CSM y. CSM y. I'm going to double check that with Python Tutor, and then I will get back to the next question. Okay, I think that looks correct. So let's do the next part. So the next part is using lists. Appending, extending, all that. I believe that was midterm 2 stuff. I don't fully remember. But yeah, let's get into it. So maybe we should quickly go over what append and extend do, and then we'll do this. So let's say I had this list 1, 2, 3, 4, and I bind it to some variable list. Okay, calling append on the list will create a new box here, and then add whatever element I pass in to append. So if I just pass in 5, then this list will become a list with 5 at the end. Alternatively, if I passed in, say, let's say I create a L2, and that's just like some list 1, 3. So in my environment diagram, L2 points to this box here. Then what I'll do, let's say I call list.append L2. Then I copy the arrow from L2 and I put it in this new box. So arrows are always copied and elements are always just, everything is always copied, yeah. But when we have lists, then we copy the arrows. So yeah, the key thing is that append is just going to add one element to the end. Now let's do extend. Extend takes in an iterable, and commonly we just pass in a list. So if I was to extend this with the list, like, okay, once again I'm going to do an environment diagram so we know exactly what's going on. So list 2, let's say, points to this list 1, 2, 3, 4. Okay? And what append would extend would do, if I did list.extend list 2, it would look at each element in list 2 and then make a box in list for that element. So we'd make a box, we'd copy the first element 1, then we'd make another box, copy the 2, and then make a last box and copy the arrow from the third box. Yeah, that's what extend does. All right. So we make this list ghost. Okay, so let's have our global frame here. And ghost is pointing to a list. The first element is 1, second element is 0, third element is a list that contains a 3, and the last element is a 1. Then we define some function boo, func boo that takes in a parameter spooky. I don't know why we're still doing Halloween themed stuff, but okay. And then its parent is the global frame. Sorry, I messed up my alignment here. Let's do it under. Okay, parent is the global frame. And then I say pumpkin is equal to the result of calling boo on ghost of 2. So I open a new frame, And okay, let's just leave this pumpkin hanging here. It's going to be something. So I open a new frame, F1, for boot, parent equals global, and the parameter that's passed in is ghost of 2, which is this list 3 right here. So what's that parameter called? That parameter is called spooky. And it points to this list here. So once again, I copied the arrow. Okay. Now we say ghost.append spooky.append ghost. So spooky.append ghost would say, okay, spooky is this list here, this with a 3, and we append, so add one box, and we just append ghost to it. So we look up the name ghost. It's not in our frame F1, so we actually use the ghost in the global frame. So now we just append and we add an arrow. So we copied this arrow from ghost here. It points to the same thing, and that is our list. Then we say ghost.append, whatever this returns. So one more thing I didn't mention was that most of these like list mutation functions don't return anything. So append, extend, I believe remove also doesn't return anything. Let me just double check with Python once for remove. Yeah, remove also doesn't return anything. So it's just pop that's returning things. So if it's not returning anything, that's the same as returning none. So we're going to append none to ghost. So another box that just has none. All right. Then we reassign spooky to this complicated thing. Cool. So spooky's arrow will be pointed to spooky. So spooky is just our list of ghost of 2 of 1 of 1. Okay, so let's figure out what that is. Ghost of 2 is ghost of 0, 1, 2. So it's this arrow right here. Of 1, so this is this arrow right here. So all the way back to ghost. And then we want the first element of that list. So that's a 0 because it matches the 1 here. I hope my circles made sense. So let me draw a line here. So this thing, entire thing, is just a 0. And we're saying spooky is equal to spooky of 0. Spooky of 0 is just a 3. So spooky is now 3. All right. Then we say, okay, make a copy of ghost and extend it with a list that contains spooky. Okay, so we make a copy of ghost, and that would mean that, and this is slicing. Slicing always makes a copy, I guess I didn't mention. And with no parameters, slicing will copy the entire list. So we make a list with 1, 0, and then we copy the arrow, and then 1, and then none. And we're extending this list with a list that contains spooky, but we actually don't need to do this because yeah, this is just not going to be part of our environment diagram. It's just this random list that's not assigned to any variable because we just made a copy of ghost. So we're not reassigning anything we care about. So I'm just going to stop here. Okay, then we say we reassign spooky again, and we reassign it to this list whose first element is a list with spooky, so that's 3. And then we add, and adding is just the same as calling extend. So we add a list that contains ghost of spooky minus 1 dot pop. So ghost of spooky minus 1, so ghost of 2, which is going to be this list right here, and then we pop that. So popping that would mean removing that from, popping removes the last element from a list. So popping this element would just mean deleting this arrow right here and then removing this. Okay? And pop actually does return something. It returns the element that it just popped off. So it's going to return this arrow right here. And what I'll do is I'll just copy that arrow over, and remember we made a list that contains this arrow. So we made a list that contains this arrow. So we're adding both of these, and that just means we get a 3 and then a box. Let me just do it here. A 3 and then a box that points to this list. And then I'll delete my other arrow because we don't need that anymore. Okay, and if that didn't make sense, let's do an example of adding things. So if I were to add these two things, then I'd start with a 3. I'd make a copy of that, and then I'd add the first element from the other list, 1, then the second element, 2, and then the arrow for the third element. So in our case, we just had to copy one arrow. Okay. Now we've reassigned Spooky, and we're on the line ghost.remove 1. Okay. So ghost.remove 1 will remove this 0 from ghost. Oh, sorry, this 1 from ghost. And it's just going to find the earliest one. So it'll remove this 1, and I'm going to use my other eraser here. Okay. Okay. So this is erasing rather slowly. All right. So I want to get rid of these indices here because they're not the same anymore. Okay. So we remove the 1, and remember remove actually returns none. So that means that we've removed the 1, but then we're calling ghost.remove on a none. So that means we remove the none from ghost now. So once again, let me switch to my other eraser. Okay. So we remove the none as well. And then we seem to have this random arrow here, which doesn't really matter. And then I'll extend this one all the way. Okay. The last thing we do is we do spooky plus equals happy Halloween. So that means we create a list with happy Halloween, and then we extend spooky by that list. So that just means adding an element here that says happy Halloween. Okay, and lastly we return spooky. So return value, one thing I messed up was there's an arrow here, and there's an arrow here as well. That's what we return. And then we say pumpkin is pointing to the same list. So yeah, that's that one. Let's take a look at the answer key. Hope I did not mess up, but yeah, I'm just going to pull up Python Tutor real quick. Okay, so ghost points to a list with 0, then a list with 3, then 1. Shoot, I think I did mess up somewhere. Pumpkin points to a list with, oh, okay, so yeah, I just messed up at the last step. Instead of appending happy Halloween to spooky, I accidentally appended it to ghost. My bad. Okay, so this goes erased, and then instead I want to extend this list with the list that contained happy Halloween. So spooky and pumpkin both now have happy Halloween. Yeah, I think that's it. Let's do the next one. Oh, sorry, answer key. Look away, I guess. Let me just erase this. Okay. So suppose the position of the rightmost digit of a number is defined as 1. The position of a digit increases from right to left. Fill in the function that takes a non-negative integer n and returns a non-negative integer. For each digit d of n, positionizer either changes d to be the remainder of d divided by its position, or leaves D the same if it is equal to the position. Okay, let's figure out what this means. So we have 1, 2, 3, 4, 5 as an example. And they said the rightmost digit is position 1, and we go position 2, 3, 4, 5, just like that. Then they said if D is equal to its position, so D is 3 and the position is 3, then we don't change it. Otherwise, if we have a digit that's not equal to its position, so all of the other ones, then we reassign that digit to the remainder of D divided by that position. So this 1, 2, 3, 4, 5, well, the 5 would become 5 divided by 1, and the remainder of 5 divided by 1. So that would just be 0, because 1 goes into 5. 2 goes into 4, so that would be 0. 3 is unchanged, and then we do the remainder of 2 divided by 4. That's a 2, because 4 is larger than 2. And then this one is a 1. So another way of saying the remainder is just use the modulus operator, because this is all non-negative integers. So yeah. All right, let's see what we have. So we have this helper function in here that takes in n and a position. So that seems like it's going to help us keep track of where the position is, like whether we're at position 1, 2, 3, 4, or 5, so on. And we call this helper in the end. So let's first just kind of call this helper. So we haven't done anything to n yet, so that'll just be n. And we can start off at our position at 1. The reason I started at 1 was because, in my opinion, the position can be the position of the rightmost digit. And the reason that is because we typically in these problems just deal with the rightmost digit, because we know how to get that. We just do n mod 10. So yeah, that's an easy way to do it. And I mean, if you're having trouble figuring out where to start, 1 is a pretty good place. Okay. So let's figure out what this function is doing. So there's two cases. One is where if n mod 10 is equal pos, so that's going to be our case with the 3. So that means that we have some like number rest, and let's say that's like sort of the solution of the rest of the problem. So if we just had this like 1, 2, 3, and the solution was just 1, 2, right? Let's say our rest kind of holds some number such that if we add it to 3, then we get our answer. So in that case, our rest would actually be holding 120 here. Because yeah, we're kind of limited here because we only have this plus. We can't manipulate rest. So rest is going to have to be 120 here once we're at digit 3. Then what we do to 120 is we just add 3 because 3 remains unchanged. So this is 120 plus 3, which is 3 is just the last digit, n mod 10. If you're having trouble seeing why 3 would be the last digit, I kind of skipped a step here. This step I skipped was that the number we'd be passing would actually just be 1, 2, 3 by the time we got to this call. So this was a weird place for me to start. I'm sorry about that. Okay, so let's go back to our original example. So at the beginning, the digit that we're actually checking is this 5. So is this 5 equal to its position? It's not. So what do? We somehow call our function, get the answer for this 1, 2, 3, 4. So we get 1, 2, 3, 0. And then we combine it with 5 in such a way that we get 1, 2, 3, 0, 5. 1, 2, 3, 0, and then whatever we want for 5. What do we want for 5? We want 0, because 5 mod 1 is 0. So that means we're going to be adding 5 mod 1 to rest. So 5 mod 1 is, we first get 5, which is the last digit, and then mod it with the position. Then what do we do to this 1, 2, 3, 0 for it to actually work? Well, we actually multiply it by 10, so we just add a 0. So that tells us like what our rest is going to be. Our rest is going to be a call to the helper with n floor div 10, so with 1, 2, 3, 4. But what do we want to do to position here? let's think about that. So we said the rightmost digits position here was 1 for 5, right? For 4, we actually want it to be 2. So this is the way. This is how we're actually gonna like stay consistent and make sure the 2 is always like position 2 is always this number 4. Position 3 is always this number 3. So we're actually gonna increment the position here. So that means that when I call this helper on 1, 2, 3, 4, I'll call it with the position 2. And that maintains this consistent labeling of 2, 3, 4, 5. And that's important just because we know like what to we need to know like what to divide by and like when not to divide. Okay. But remember that this helper is just going to return the answer of calling the helper on 1, 2, 3, 4. So that would just return 1, 2, 3, 0. We want to make it so that when we add it to the last digit, we get our final answer. So we have to multiply this by 10. And that can be our answer, rest. That can be our variable rest. The last thing we need to do is figure out a base case. So I think a very simple go-to here would just be, okay, when are we done? We're done when we have no more digits, and that would be when n is 0. What do we want to do with it when n is 0? Well, we don't want to add anything to our answer, so we can just return 0. And this is not something, like this n equals 0 thing feels sort of like a guess. So let's try to, say, verify it. So let's say we had, let's just verify the whole thing. Let's say we had a number 23, right? And the digits are 1 and 2. Oh, sorry. What we do here is we say, okay, rest is equal to the result of calling helper on 2 with position 1. That just means, it's position 2, sorry, because we incremented the position. That means this 2 remains at position 2. Okay? And what do we want this to return? We want this to return a 2, right? Let's see how we would evaluate it. So when we're evaluating it, we'd say, okay, we'd find the rest in its frame. And we'd say, okay, so we're evaluating 2, 2. And rest here is equal to the result of calling helper on 0, which is 2 floor diff 10, and 3. Well, that means that we add rest to like our last digit, right? So in this case, we're going to add rest to 2. So we want to do rest plus 2 is equal to 2, right? So the answer for when we pass in n equals 2, and it's at position 2, that's just the number 2. And so what do we want rest to be? We want rest to be 0. So we want this helper of 0, 3 to return 0 when n is 0. So that's how we get our base case. And yeah, just for the sake of completion, this rest is now helper of 0, 3, and then we return 2. So this helper of 2 will return 2. That means that it's the rest here, but remember the rest is the helper called times 10. So the rest is 2 times 10, and then we add 3 mod 1 to that, and that's just 0. So that will give us 20. Yeah, so that's that problem. I feel like I did not do a great job explaining that, but I hope you got the gist, and I hope the next one goes better. Yeah, let's go to the next one. Okay, so sorry, I have some drawings. I just did this one in section. Okay, so Now we're filling in the max positionizer function, which takes a list of digits and it returns the k-digit number with the highest value when positionized. The digits must stay in the same order. Example, for k equals 2, you can't form 21. So what that means is that returning k-digit numbers, so let's say like k was 2 as they described, then for the list 1, 2, 3, the k-digit numbers formed would be 12, oh sorry, it's not 1 comma 2, 12, 13, and 23, right? So those are the three k-digit numbers. And then we say, okay, we want to figure out the k-digit number with the highest value when positionized. So we want to call positionize on each of these. So we know this one gives us 20. This one, does it give us 10? Perhaps? And then this one, let's say it gives us 12. And then we want to return the value that's the largest when it's positionized. So here, the largest positionized one is 20. So we want to return the value associated with it, which is 23. Okay, and we actually have a hint here, which is pretty helpful, where we're using the helper to create a list of all possible k-digit numbers formed from list. Great. So that means that we can sort of just fill out the end of this function already, because this helper is going to return this like list that we want of this 1, 2, 1, 3, and 2, 3, and we sort of just have to get a max from that list. So at the end, I can just call max on the result of getting all the possible numbers of size k from list. But I don't actually just want the max, because not in all cases, it's not going to always be the case that like the largest number in the list has the largest positionizer value. So I actually want to somehow like make it get the max of the positionizer values and then return the like element in the array that led to that max. So to do that, we can use this key function. So the key function, what it does is it calls the function. The key argument is called on every element of this list. So it'll be called on this 12, then this 13, and this 23. And that's actually used to compute the max, as opposed to just using the numbers themselves. So as an example, let's say I had this list 1, 2, 3, and I wanted the smallest number, but let's say I was only allowed to use the max function. So then I'd call max, and then I'd pass in a key equals lambda. So a key is a one argument function that sort of returns like, oh, like the value of each element. So let's say the value here is negative x. So what that would mean is that this essentially reverses the values for each one, like the priorities, because 3 would then be like a negative 3, right? 2 would be a negative 2, and 1 would be a negative 1. So this would choose the largest of these, which is the negative 1, which happens to be the smallest in our list. So calling this would just return 1. So similarly, we want to do the same thing, except our key is not this like other lambda function. It's just this positionizer function that we had in the previous part. That's also a one argument function that you can apply onto each element of the list. Okay, so we figured that out. Now let's do this actual function. So make nums, remember, is just returning the list of numbers. So one more time, we have 1, 2, 3, and we want 12, 13, 23, but we don't want something like 21 because it goes in the reverse order. And that actually helps us a lot. So if you haven't thought of this already, this is going to be like count partition style, because essentially we have like a limited number of elements that we want to include, and we have two choices. The choices are, do we include the current element or do we not? So I'm going to make this tree here, and let's say on the left side of the tree, I say, okay, include the first element. On the right side, I say I don't include this element. And that actually gets me all the possible k-digit numbers, because either either the number is going to have a 1 at the front, or it's not going to have a 1 at the front, right? So let's see what our recursive call is going to be if we didn't want a 1 at the front. Well, if we don't want a 1 in the front, then we can just make a recursive call to our function makeNums. Let's see what it takes. It takes k and a list. So let's say we started with k equals 2. So since we haven't actually used any numbers, that means we still have 2 more numbers to use, right? So we're going to have k still remains 2. But we said, okay, we don't want to include this 1. And a way to signify that, a way to do that is just not include the 1 in our list anymore. So this means remove the first element from our list. The other one is a bit complicated, or a bit more complicated. But one thing we still need is this call to make numbers with the truncated list. Because we've used this 1, so we only have the remaining ones left. But our k is now 1. Why is k 1? It's because we've already included one number in our number. Okay, so this mn of 2, 3, 1 would return a list that has 2 and it has 3. Right? And what do we want to do? From this, we want a list that has 12 and 13, because these are the ones that have 1 in them. And then from this one, we just want 23. Right? So let's figure out how to do the left one. So the left one, we have this list of 2 and 3, and we have like what goes at the front. So we have like 1 here, right? And let's say I just want to combine like 1 with, say, this 2. So I say 1 and 2 combined should give me 12. Well, what do I do to 1? I can just multiply it by 10 to get 12. But that doesn't always work. What if instead of having this list of 2 and 3, I had a larger list with, like, say, the 2-digit numbers, so 23 and say 46. This is a separate example. And then I wanted to add 3 to the front of it. So I wanted 323 and 346. Well, in that case, I can't do 3 times 10 plus 23, because that's not equal to 323, right? But I can do 3 times 100 plus 23. And the way I get like this number without sort of guessing is to use the fact that we have k digits in our number. So k is equal to 3, and 3 is at the front. So we want to multiply by 3 by 100, because 100 is a 3-digit number, because that'll just make 3 300. And the pattern here, which you can just figure out by trying this, is 3 times 10 to the power of k minus 1. So if we did k equals 3, this would be 3 to the power of 10 squared, which is 3 times 100. And it works in our earlier example where k equals 2, where it would just be times 10. So now that we have this pattern, that's what we want to do for an individual number. So we do 1 times 10 to the k minus 1, and we want to combine that with each of the elements in this list. So we don't want to just add it to like this list itself, but we want to make a new list where each element of that list is this thing, so like 10 plus 2 and then 10 plus 3. And that we can accomplish with a list comprehension. So let's go back and see what we can do. So B, we said, was just the result of calling make num on the list without the first element and the same k. And I just got that from our other branch here. A is doing some list comprehension, which does for rest in something. Well, the rest of our number is just going to be everything but the first digit. So that's going to be our recursive call again. So mn of list sliced, but k minus 1 because we just used up a number. So that's our recursive call. And remember, this would give us something like a list with 2 and 3. So for each of these elements, we want to create a new element, and that element is the first element of our list times 10 to the power of k minus 1. And the way I do to the power of is I use 2 asterisks. They would probably remind you of something like this on an exam. And then plus rest. So as an example, this would be doing 10 plus 2, or 10 plus 3. Okay, and then we just return the sum of both those lists. So that's like our solution here. We just have to figure out the base cases. And I think the base cases are also pretty tricky in this problem, but let's try to make some guesses and figure it out. All right. Let me try to clear some space. Okay. So one base case that we can figure out is by looking at like what could go wrong if we had like a weird k or a weird list. Well, we're making these calls like list of 0 and like list splice, right? We can't do this if our list doesn't have any elements. So one idea that I have is if empty list. So that's one base case, I think. The other base case that I thought of was what happens like when we don't want to include any more elements. So for example, if I had this like 1, 2, 3 with k equals 2, and I already had this like 12, right? Let's say my 12 was like, I had already formed, and then I had called make number on this list of 3, and k equals whatever, 0, right? K is 0 because we've already used up 2 elements. Well, in that case, we don't actually want to include this 3, right? Because we've already used up 2 of our elements, and that's all we needed. So I think that's going to be our other base case. So if k equals 0, we do something. And if the length of the list is equals 0, we return an empty list. So yeah, if there's nothing in the list, then you can't add any more elements. Okay. All right. So what do we want to do when k equals 0? So let's go back to this example here. I wrote it a little misleadingly because you're not going to be doing 12 plus like the remainder. But let's say you go down the left side of each branch. So you include, and you get 10 plus everything in that 2 and 3, right? But that 2 and 3 is actually going to be formed by a recursive call. So that would be namely mn of 2, 3 with a 1. Okay, so I go left again in this call, and then I say include the 2, and that would be 2 plus mn and of this list with 3 and 0. Or more specifically, we're going to add 2 to the front of every element in this list. So this is actually going to be like a list. Sorry. So let's go back and look at like what our A is. Our A is adding this 2 to the front of every element in this call mn of list sliced at 1. So that means that this has got to return a list. And what's going to be in that list? Well, it can't be empty because I do want this to return a 2, right? But it also can't have any number like, say, like 5, right? Because that would do like, oh, 2 plus 5, which is 7. That's not what I want. So what can I put in here such that this 2 remains a 2? That'll be a 0. So in my other base case, I can just return a list with 0. And then, yeah, this just returns 2. And then this does 10 plus 2. So that would give us a list whose first element is 12. And then the second element would just be from the other branch, which would be like not including the 2. Yeah, and then, yeah, so that would end up becoming a 13. And that's it. That's make nums. I hope you found it helpful. I will probably take a break and then come back and do some object-oriented programming.